Hi and welcome to this Transition Year Higher Level Maths Sequence and Series Revision Module video. So this is part of the Sequences and Series Revision Module, which consists of 3 videos which will help with revising what you've already covered at the Junior Cert Higher Level course, and we'll be building on this as we move into the Leaving Cert Higher Level Maths course. So this video is going to cover linear sequences and will include looking at number patterns and the terminology which goes along with them, identifying an arithmetic sequence, using the term-to-term rule for arithmetic sequences, using the position-to-term rule for arithmetic sequences, finding the general rule for arithmetic sequences, and number sequences from patterns. So let's just talk a little bit about number patterns. So here we have a number pattern which is 8, 13, 18, 23 and 28. Each of those numbers is called a term. So we could write that as the first term, second term, third term, fourth term and fifth term. The other word that we need to know is difference. So the difference between each term in this case will be called the first difference, and if that's the same then it's called the common difference. So let's talk a little bit more about that. So here we have the same sequence, 8, 13, 18, 23 and 28. Instead of writing the first term, second term, third term, etc., we have simplified it to T1, T2, T3, T4, T5 and so on. So we're going to use more specific or mathematical terminology. Instead of saying a linear pattern, we're going to talk about this as an arithmetic sequence. So arithmetic is another way to say linear, and pattern is pattern is a more encompassing word for sequence. When we talk about numbers, we tend to call it a sequence. A pattern tends to be more about pictures, and we'll see how the two relate later in this PowerPoint. So here we have our sequence, and we want to know, well, how do we identify it as an arithmetic sequence? So let's first of all figure out what the first difference is. So what do I add to get to the next term? So what do I add to 8 to get to 13? So I add 5. What do I add to 13 to get to 18? I add 5. What do I add to 18 to get to 23? I add 5. And what do I add to 23 to get to 28? Again, that's 5. So that is what we call the first difference, and because that is the same, we call that the common difference. So it has what we call a common first difference, and that is how we identify an arithmetic sequence. If a sequence has a common first difference, then it must be an arithmetic or linear sequence. Let's take a second sequence. T1 is 200, T2 is 185, T3 is 170, T4 is 155, and T5 is 140. You might notice at this point that this sequence is getting smaller or is decreasing. Let's talk about the first difference. So again, what do I add to 200 to get to 185? Well, I can talk about this as adding a minus 15. Same here, I add a minus 15, I add a minus 15, and I add a minus 15. And again, we have a common first difference. So this is an arithmetic sequence, or we can call it a linear sequence. So let's talk about the term-to-term rule for sequences. So if I was to ask you to write a linear or an arithmetic sequence, I need to give you 2 pieces of information. I would need to tell you what the rule is. So what do you need to do to get from one term to the other? We call that our difference, and the other thing I'd need to tell you is where to start. So the term-to-term rule is where you're given at least one term and the rule. So let's take an example. So the first term is 7 and my rule is add 9. So if I wanted to put together, I would talk about T1 is 7 and I want to work out, let's say, 5 terms. So we'll go up to term 6. So 5 more terms. So they've given me the rule and they've said we add 9. So they've given me that part, and I need to figure out, well, what are my next few terms. So here I get 16, 25, 34, 43 and 52. So this is how we can generate the sequence of numbers. So it's important to remember that it's not enough just to know the rule, the add 9, you also need to be given at least one term. You don't have to be given the first term, you can work backwards, and we'll see how we can work with that in the next slide. So in a particular linear sequence, the second term is 40 and the sixth term is 116. Fill in the boxes to show the rest of the 6 terms of this sequence. Okay, so it's important that they've told us here that it is linear or arithmetic, so therefore I'm adding on the same number here each time. Okay, so I know I'm adding on some number and I'm going to call that D. Okay, so I'm adding on D. Now, I don't know D, but they have given me 2 terms. So I'm going to say, well, if I want to jump from 40 all the way to 116, I know what I have to add. So I do 116 minus 40 and we get 76. So I've added 76 here. Now we know that that big jump we have here, that big red jump, is the same as 4 little green jumps. So if I divide 76 by 4, we can figure out that each jump should be 19. So simply we are doing 76 divided by 4, and that gives us 19. So we have, again, 4 jumps, 2, 3, 4, and they, when added together, would be the same as jumping 1 jump of 76. So now that I know all that information, I can use it. So I actually had a plus 19 here. So what number did I add 19 to and get to 40? Well, I'm kind of working backwards here. So I do 40 minus 19, and we get 21. Now we're going to work forward, and one way we'll know we're correct is we can work out our final number here, and if it doesn't add to 116, we know something has gone wrong. If it does add to 116, we know everything is okay. So my next number is 40 plus 19, which is 59. So then we have 59 plus 19, and we get 78. And then we do 78 plus 19, and we get 97. And if we do 97 plus 19, we end up at 116, so we know that everything has gone right. So it's not necessary to have the first term. We might be given a term in the middle, and also if they give us 2 terms, knowing that it's a linear or an arithmetic sequence allows us to figure out that rule or what that common difference is. So now let's talk about the positioned term rule for sequences. So a positioned term rule is a rule that can be used to generate any term in the sequence given its position. In the last slides, we were working with the term-to-term rule, and that's nice for building up the first few terms of a sequence. But what if I wanted to know what's going to happen to the 100th term, or the 200th term, or the 1000th term? We're going to be adding and adding and adding for quite a long time. So this is where we get a more efficient method, which is the position-to-term rule. So this is more commonly known as the general term, or Tn, or the nth term. So you'll see that as we work through, we're going to work a little bit with your formula and log tables. So you're going to be able to see that it is called the nth term in there. So for example, they might give you something like this. So that is Tn is equal to 2n plus 5. That is the general term. So what we can work out from here is I can say, well, T1 is equal to 2 times, instead of n, I'm putting in 1. So notice that there's my 1. So in my formula, there were my n's. I'm now replacing them with 1's, plus 5. So my first term is 2 plus 5. My first term is 7. I can jump even further. I can say, well, what about my 10th term? So instead of having to do all the terms in between, I can go straight to my 10th term. So I get 2 times 10 plus 5. And I'm just showing in red so you can see that substitution, which is 20 plus 5, which is 25. So a much more efficient method for when we're dealing with terms later on in the sequence. So now let's use this general term some more. The general term of the sequence is given as Tn is equal to 5n minus 3. Find the first, the third and the seventh term. So we're looking for T1, we're looking for T3 and we're looking for T7. So we do 5 times, instead of n we have 1 minus 3, which is 5 minus 3, which is 2. Here we have 5 and we're subbing in 3 instead of n. Minus 3, 15 minus 3, which is 12. 5 times 7 minus 3, which is 35, minus 3, which is 32. So we have our three values of the first, the third and the seventh term very quickly using that general term. So how would we work out the general term or the nth term given a sequence? So working backwards. So the first 5 terms of the sequence with the general term, Tn is equal to 6n minus 2 are 4, 10, 16, 22 and 28. So what do you notice about these terms? Well, the first thing I'm going to do is I'm going to write them out like this. 4, 10, 16, 22, 28. And I'm going to check the first thing that we will always check when we're dealing with the sequence, and that is my first difference. What do I do? So I'm adding a 6 here, adding a 6, I'm adding a 6, I'm adding a 6. Okay, so we have a common first difference, and that common first difference is 6. Now, take a look at that common first difference and let's go back to the formula that they gave us, or the general term. Notice, and it's not a coincidence, that this common first difference, which is 6, appears as the coefficient to n. So that, like I said, is not a coincidence. And then the minus 2 is the correction that it would need. So let's take a look at how we could use this to our advantage. So we're going to work two different ways of finding the general term or the nth term or Tn of an arithmetic or linear sequence. We're going to use a table and then we're going to use the formula that are given in the Formula and Tables book. So example 3, find the general term of an arithmetic sequence, and we're going to use the first method, which is a table. So given the following sequence, find the nth term. So we have 26, 23, 20, 17 and 14. We notice that this is a decreasing sequence, it's getting smaller, it's descending. So we know that we're going to have to make it smaller. So what I'm doing each time is I'm adding a negative 3. And that is our common first difference. And we'll notice as we work on the next two videos that are dealing with different types of sequences that we're still using the same method. We're still using this idea of the differences of the term as our go-to. So we have a common first difference, which means when I have a formula, which is going to be Tn equals, it's going to be minus 3n plus some number. Okay. So what I'm going to do is I'm going to say, well, look, if I have Tn as minus 3n, so here I have minus 3 times 1, which is minus 3, and here I have minus 3 by 2, which is minus 6, and minus 3 times 3, which is minus 9. So just make sure you're clear. That 1 is coming from, it's the first term, this 2 is coming from the fact it's the second term, 3 is coming from the third term, and so on. Minus 3 times 4 is minus 12, and minus 3 times 5 is minus 15. Now, what correction will I need to add to each of those to get to my number? So I'm at minus 3, and what do I have to add to get to 26? So in this case, I'll add 29. Now, when I look at the rest of them, I do the same thing. So what do I add to minus 6 to get to 23? And it's 29. And what you should find is that piece there remains constant. It's the constant piece. So we have that plus 29, plus 29, plus 29. So that gives us our formula as minus 3n plus 29. So that is the table method, which can help us work out the general formula, or Tn, for an arithmetic sequence. So the next method we're going to look at is going to be using something from your log tables. So here is the sequences and series page. On the sequences and series page, we're dealing with the arithmetic sequence up here, and we're looking at this formula for Tn. So Tn equals a plus n minus 1 times d, where a is the first term and d is the common difference. And they've also given us up here, Tn is the nth term. So you'll be using all this page as you move into Leaving Cert higher level. For the moment, we're going to look specifically just up here at the arithmetic sequence part. And this is why I've been using the term arithmetic as well as linear throughout the whole video, because if you want to use your log tables, you already know this word here, and you're not wondering where is my linear sequence. So let's do another example. I've taken the exact same sequence as before, 26, 23, 20, 17 and 14, because I want you to make a real judgment on which method you prefer. And we're going to use the formula which I have here. So again, the first thing I'm going to do is I'm going to figure out that my first common difference is minus 3, my common first difference. And they've said, just come back up here to my formula, that d is the common difference. So I need to work out a and I need to work out d if I want to use this formula. So my formula wants a, and my formula wants d. So a is the first term, which in this case is 26, and d is the common difference, which is minus 3. I then write down my formula. Tn is a plus n minus 1 times d. So Tn is equal to 26 plus n minus 1. We're not subbing in for n. Remember, this is the general term, so we want n in our answer, times minus 3. Tn, if you find it easier, you can switch the order of those brackets, because multiplication order does not matter. So we can do minus 3 times n minus 1. So Tn is equal to 26 minus 3n plus 3, watch your signs, and our final answer then is Tn equals minus 3n plus 29, which is exactly the same answer that we got when we worked through using the table method. So it is 100% up to you which one you prefer. Both give the same answer. So now let's look at a number sequence which we take from a pattern. So often we are given a pattern of shapes and or colours for which we can create a number sequence from. So look at this example. We've got a series of dots. So stage 1 is a single dot, stage 2 is 3 dots, and stage 3 is 5 dots. So this represents the arithmetic sequence 1, 3, 5. And if you want to go a step further, you could say that you're adding 2, you're adding 2, and we can work with that. So let's take another more complex pattern. So here we have some shapes that have 2 different colors and a shape. So the first sequence you could be asked is, what's the sequence of the number of yellow blocks? So that's 1, 2, 3. You could be asked, what's the sequence of blue blocks? And that is 6, 10 and 14. And then the third sequence is the sequence of the total number of blocks, which is 17, 12 or 17. So sometimes a question can ask you to do a sequence based on multiple elements of a pattern. So make sure you're reading the question very carefully to understand which element you are being asked about. Example 5, finding the general formula of a pattern. So find a formula that describes the number of triangles in the pattern below for any given figure. So here again, there's kind of multiple shapes going on, and they've asked us specifically for the number of triangles. I'm going to work with the formula from our log tables, just because I find that a little bit more efficient, but if you prefer the table method, please go ahead. First thing we're going to do is we're going to write down the number of triangles as a sequence. So we have 1, 2, 3, 4. So very straightforward. And what we can do is we can very clearly see that our common difference here is +1. Now at this point you might be able to go, oh, I know exactly how to do this, and that's fine, but I'm going to work through the long way. So first thing I do is identify my first term. I identify my common difference. I say Tn is equal to A plus n minus 1 times D. So Tn is equal to 1 plus n minus 1 times 1, which is 1 plus n minus 1. So my Tn is simply n. And you might see that in the first pattern there is one triangle, in the second pattern there is 2 triangles, and so on. So how many triangles appear in figure 15? So we're asking for T15, which is simply 15. This question could also be asked the total number of shapes, which would then change this because you're adding the little rectangle plus the triangle, so it would be 2, 4, 6, and so on.